In the last class, we did discussed about switch level modeling, all these things, right? And
Yes,
then
sir.
loops, what are the blocks, sequential, parallel, all these things we were discussed. And then today we will discuss now tasks and functions in Verilog. What are tasks and what are functions? Okay, this slide will gives you the detailed information. Okay, so I will explain one by one now. So what is the function? What is the use of that? Functions is used for quick calculation purpose. Like arithmetic operations purpose, we are using the functions. Any arithmetic operations you want to do that means then go for the functions. Just give me a minute. Now it's okay, right? Okay, so what is the use of functions? Functions are used for calculating purpose and it gives single value. It returns single value. Suppose I am returning any function. Okay, so what is the function? Function, function name. So name of the function anything. So just name only I am using, and then inside that you will use some arguments int a comma b. Okay, so then result you are writing, then result what is that, some a plus b you are doing that, and then return result. Okay, this result will come. Okay, that is the function. So function characteristics are return single value. Okay, any single value it will return that and execute instantly, because the functions are executed at t equal to 0 only. Okay, with time t equal to 0 only it will execute that, and it cannot contain any delays. This is illegal. Okay, hash 10 result equal to a plus b you return means that is illegal. Okay, it is not allowing the delays. Okay, because functions are executed t equal to 0 only. So all the expressions, whatever the expressions we are using that, so cannot contain any delay. Okay, cannot contain any delay used inside the expressions. Okay, any expressions you are using means that expressions cannot have any delays. Okay, so this is the syntax, basic syntax of my function. Just writing the function, what is the function name. Okay, function, and return type. That return type is maybe either integer or bit or byte. Okay, any data type you can write that. Okay, so return type and your function name. Sometimes I will write the function arguments inside this name. Okay, or otherwise I will write individually, like input argument, some statements, and then return value. In this way also we will write like a module. Okay, how we are writing the module? Suppose module, some half adder you mentioned. Okay, so inside that you are writing a comma b comma some comma carry. Okay, this is also correct. Okay, or you will write module and then half adder, same thing. Okay, so then I am writing the inputs here. So input y a comma b, and then output range some comma carry. In this way I have written. Okay, so this is also correct. Same way function, in function also we will write function return type and then function name. See the function some integer and then name is maximum value I want to return that. Okay, maximum value I want to return that, and so just semicolon it separates that ending of this statement. After that, input. Inside the input, A is taking and B is taking, and then output you will take that. So output and then statement. What is the statement? So max value I want to get that. So max value, for this max value I am initializing some value, initializing to B or something. Okay, then condition I want to write that A greater than B I have written, then return max value. Okay, so if this condition is true, A is the maximum value, otherwise B is the maximum value. Okay, so in that way I am just writing some piece of code related to function. Okay, so that's what. And then we have some comparison logic also. See, just example for the function. I told you, function, and then integer is a return type, and then comparison operation he is doing that. Int a comma b. Okay, inputs he is written a comma b. So comparing that. If a equal to b, so comparison logic means either greater than or less than or equal to. Okay, so this comparison logic we are applying here. See, why no delays are allowed in the functions? Okay, functions are always used for combinational circuits. Okay, combinational circuits A and B, we are giving the input, immediately I am getting the output A and B. Or I am giving some OR gate A and B, I am giving the inputs, I will get the output immediately y equal to A plus B. Yes. Without any delay. Okay, without any delay I will get the output. So because this combination logic should respond immediately. Okay, that is the reason functions cannot contain any delays and wait statement and then passage or negate clocks. All these things are not there. Suppose you are writing at the rate passage clock. Okay, so in modules it is allowed. This is event based controlling, right? So in module it is allowed, but in that functions we are not writing any wait statement. What is the wait statement here? Suppose wait condition is there, wait a equal to 5. Up to that 5 is reached, then only it terminates the loop, otherwise it is stayed on the same loop. Suppose a equal to 3 only we got that, then still it is waiting there and then updating the value. After some delay, okay, so then a value will be become 4, still it is in wait condition only. Okay, so because it depends on the delay, wait condition is depends upon the delay. If you are giving the delay value, then only we are going to the next state. Okay, so then this wait is operating like a if condition. But what is the main difference in this if condition? If the condition is true, okay, true statement will be executed, dollar display. Okay, then true will be executed. Okay, otherwise else condition it is going there. If condition is false, then it is going to the other path. Alternative path is there. Okay, in that alternative path, it will display that output. But wait is not like that. Okay, so if the it is waiting for the same condition, whatever the condition you are written inside the wait keyword. Okay, so then whenever it occurs that condition, then only it terminates the loop. Otherwise, it not terminating that. Okay, see, I told you now functions are not allowing the delays. Okay, that is the illegal function example. Function addition I am doing that. Okay, so just he is writing add function name, but he is comparing, assigning the values a equal to b, just copying the values, b value is copying to a. Okay, so end function, but this delay is not allowed here. The ultimate aim is functions are not allowing any delays. Okay, delays are not allowed. Why functions can be used directly, like we can call sum equal to add a comma b. Add is a function name, right? We can call the function name. Okay, it returns the value. What is the value it returns? Add function some value, it will be returns there. Same way, task is a powerful tool, so it can consume time also. Not like that, it's unlike functions. Okay, so functions cannot allow any delays, but tasks are allowed delays. Function return only one value, then task will return multiple output values. Okay, and then tasks are also allows delays and event controls. Okay, so here previously functions are not allowing this at the rate, passage clock, all these things, right? Okay, so now this passage clock and then wait conditions and then delays all are allowed in the task. Okay, and one thing, function can call function only, cannot call task, but task can call functions as well as task. Okay, you have written any function, suppose function add function you have written. Okay, this add function we can call in the task add, or task some subtraction you will return, and then some add function we can call it here. That is possible inside the task, we can call the add function. Okay, but task in function, this task cannot be called. Okay, subtraction is not calling in the function, because in this task we have delays and then multiple return values, and then these tasks are executing at different intervals of time, all these things. Then functions are not allowing that. And functions are used for combinational circuits. Okay, combinational circuits are producing outputs immediately, but tasks are used for combinational as well as procedural also. Okay, so it is performs that procedural operations. Okay, mainly used for procedural operation, like flip flops and always. So procedural means what? Always at the rate. Okay, this always at the rate will allows you changes in the inputs, then every time it will be getting some output. And then after the always we can also use that initial begin. Okay, so maximum, that's why functions are used in RTL side. Okay, we are using these functions are in RTL side, and then tasks are used in TB side, test bench side, because this initial begin, all these things are not synthesizable, right? Not synthesizable, and then not forming any gates. But in TB simulation purpose we will use that. Okay, during the simulation purpose it is using. So this is the basic syntax for the task task name. Same thing, arguments list, input arguments, output arguments, and some statements you will write, and then ending the task. So inside the task we can write many statements, and delays are also allowed. Same thing, what you observed in the previous function is also we are using function, and some return type we have written. Okay, so this function, but here task is there and there is no return type, just directly we can write the output here. Okay, in function there is no output statement, right? So only inputs only we have mentioned, just simply written that return statement, we will write that a plus b, this output will be stored in this return type. Okay, here task we are writing the input arguments and then output arguments also. Okay, see, most of the tasks are used in test bench. Okay, so test bench purpose we are using that. and then some file handlings also we are using this task. Okay, and most of the protocols having delays. Okay, protocol handshakes and then delays and then packet generation, all these things. Okay, and then TB stimulus. These are the useful conditions of tasks.
Yes, sir.
Hmm. Say simple example. What is the simple example? Task, my task, some x equal to add a comma b. Directly we have written, right? So that is the task. Okay, this function does not allow my task inside this. Okay, and you have written the function. Suppose function, my function. Okay, so my function you have written, and then written add a comma b. I have written something, some addition operation I have done in this function, and end function I am written. Okay, this is my end function. Now I have written the task. So task, my task. Okay, so I will call this my function. Okay, so this my function I will call here. That is possible, but this my task cannot call in my function. Okay, because it is having some delay in this statement. Suppose delay I have written, then this delay is not allowed in this function. Okay, that is the reason we are not calling that function. Okay, so I told you functions and tasks in Verilog is reusable procedural blocks. We can use that. Okay, suppose we can improve the modularity and readability and then code reuse while designing a digital hardware. Okay, or and verification purpose, digital design you would design, or verification purpose. These functions and tasks are improving that procedural block level. Yeah, modular, so procedural blocks. Okay, that procedural blocks means always and then initial begin blocks we are using. Those are used to improve your modularity, scalability and readability of your design, as well as test bench. Okay, so that means we can reuse our test bench because I'm calling the functions in my design. Suppose I have written some functions. Okay, those functions will be written in my uh, module anywhere, right? So just I have written my function at the last of my module. Okay, so that function I have called in anywhere. Then you need but most of the designers, they are not writing any functions because I don't know, because I am written in somewhere else, you are calling in some other module. How can I identify where you are written this function? Okay,
Yes,
is that function is available in my module or not? I don't know. I need to search that. Okay, so that is the reason most of the design engineers are not writing any functions. Okay, so functions are used for immediate combinational calculations. Okay, so I told you, so maximum functions are used for combinational circuits, and then return single value, consumes zero simulation time, and cannot contain any delay or event controls. Already I have explained all these points, right? And then tasks are flexible for procedural blocks because that contains delays, event controls, multiple statements. And then multiple statements are not, multiple outputs are not allowed in functions. Here multiple outputs we will get. So multiple outputs we are getting that. In return in function, single value only it is written. Okay, single value only it is written. Functions are typically used for arithmetic and combination circuits. Some adder, subtractor, multiplier, some factorial number calculation, prime numbers calculation, maximum value, minimum value. Okay, anything maximum we will use the combination circuits. Okay, and While tasks are widely used in simulation generation like protocol handling, file operation, and sequential procedural behavior, all these things. Okay. So scheduling, system Verilog scheduling. Scheduling are events or regions of operations, anything they will call. Okay, all are same.
Semantics is what?
Semantic means it's a symbolic representation. Scheduling semantics, so some symbolic representation of these things. Okay. In this scheduling semantics are regions. Okay, we are having four type of regions. We are having like active region, inactive region, NDA region, and monitor region. This future region is not anything here. Okay, just for future purpose only they have mentioned. Main four regions are these regions only. What are the monitor regions? What is the use of active region? What is the use of inactive region? What happens in inactive region? And what happens in NBA region? Okay, it will allocate that non-blocking region. Okay, non-blocking assignments. In this non-blocking assignments, whatever the RHS side, LHS side is there, that will be assigned there. Okay, because why we need this scheduling means Verilog is a parallel language, right?
Yes.
Verilog is a parallel language. In this different operations, we are doing that because we are using some always blocks and then initial blocks, okay, and then we are calling some delays and then writing some statements. All these things are parallelly executing. Okay, then I don't know who is executing first. Suppose multiple initial blocks are there. Who is executing first? Or you are writing always block that is for procedural assignments because and other thing we are having some combinational also. Okay, so these are combinational circuits. So in combinational circuits, I am utilizing some assign keyword. Assign A equal to C and D. I am assigning that. Okay, and B equal to X or Y. I am assigning that. This will be. These all are executed at zero and simulation time only because all are executing parallelly. Then I need to know who is executing first, who is executing last, and who is executing in the middle. I need to know. Then that is the reason we are using this scheduling semantics because see I told you now. So many blocks are run simultaneously. Okay, like initial block, always block, continuous assignment tasks, all these things. Suppose we don't have any scheduling means I don't know who is executing first. Why we are maintaining the traffic light signals? If they don't know, they don't have any traffic signals in Bangalore means, then someone is going in this way, someone is coming in this way, and then entire traffic will be jammed. Okay, and here also I am assigning different conditions. So both are executing at the same condition, same time. Okay, so multiple drivers are occupying the same interface means they don't know who is executing first. Okay, then race condition will occur. This race conditions we need to avoid, and then some rule wise, some procedure wise, I need to execute all the statements. Then these schedulings are very important to execute your program. Okay, see every simulation time events are not executed randomly, so they execute in well defined order. Okay, so then well-defined order we are executing. That is the main idea behind this. We are studying this scheduling because the outputs may vary randomly. Okay, So outputs may vary randomly, but inputs are also executing randomly, means there is no idea here. Who is coming first? Who is coming last? I don't know. Okay, so that is the reason we need to execute all the statements in well defined order. We go for this scheduling. In this active region, why this active region is used and what type of statements is executing in this active region. Okay, most of the codes are executing in this region only. Okay, active region only. In your design code, most of the codes are executing the main executing area, and most statements begin here only. Okay, assignment statements, it will execute here only. Okay, see what happens in the active region. So block assignment simulation executes that block assignments, and RHS evaluation of non-blocking assignment. Suppose I have assigned some y less than or equal to, okay, some a into b I have assigned, or y less than or equal to d I am assigned. Okay, in during d flip flop q less than or equal to d you are assigned that. What is this RHS side d, right? This D will be executed in the active region only, but output is updated in the NBA region. Okay, there is a timeline. In this timeline, okay, so here t equal to 0 condition, this NBA region, RHS of the NBA region is updated here. Okay, here RHS of NBA region is updated here. That means D is updated here only. Okay, but that assigning of output side is taking some time. In this is the active region. Okay, this is my active region. In this active region, different statements are executing, right? What are the things are executing here? This is timeline. In this is my active region. Okay, so at t equal to 0 time it is executing that. What are the things executing in this t equal to 0 time? RHS side of NBA region. RHS of NBA is executing in this region only. That means in this example q less than or equal to d I am taking here. Okay, so d means here output, right? Sorry, input. This input is executed in this active region only. Okay, and then the output is taking some time. Okay, RHS evaluation of non-blocking assignments. This is my non-blocking assignment. In this side RHS will be executed in the active region only. And then all continuous type of assignment like assign y equal to a or b, or y equal to a and b. Okay, all these things are executed in the active region only. Continuous type of assignments, like in data flow modeling we are utilizing the continuous type of assignments, right? What are the things we are using continuous type of assignments in the data flow model? Just assign keyword we are using. Okay, this assign keyword statements all are executing in active region only. Y equal to ax or b. Okay, this will be executing. Or assign y equal to a plus b. This is executing here in the active region only. And primitives in evaluation, like all the gates. Primitives means AND gate, OR gate, NAND gate. Okay, all these are primitives in your Verilog. These are all are inbuilt. And display statements. Okay, dollar display. Okay, you are writing dollar display. What you are writing? A equal to some percentage 0d, and b equal to percentage 0d, and then writing a comma b. Okay, so these two are, these dollar statements are also executing in active region only. Okay, so these are the statements. Suppose I am executing a equal to 0, so assign a equal to 0. This also executed in active region only. Okay, and then y is less than or equal to b, so this is non-blocking region. Okay, non-blocking assignment. This is the blocking assignment. This is the non-blocking assignment. Okay, so this will be executed in the active region only, and this non-blocking assignment also executed in active region only. And dollar display statement, you are writing that. Okay, this dollar display statements are also executing in non-blocking region only. And then I am writing some combinational circuits like y equal to a XOR b, or y equal to a and b. Okay, all these are executed in active region only. Remember, clear? See, these are the examples. What I am telling. See, a less than or equal to b. This RHS is evaluated in the active region, and then actual output is happened later. That means a is updated later. Okay, I am giving the input to you, and then your output is assigning immediately or it will take some time. It's your wish. Okay, it's your wish, and wait some time for that. Okay, and then inactive region, it will execute dollar zero statements, dollar zero, sorry, hash zero delays. Hash zero delays means, I told you, suppose a swapping of two numbers, I want to do that. A equal to b and b equal to a. Okay, this gives you race condition. Why race condition is happening? You are assigning b equal to a without any delay. Same thing, a equal to b, you are executing. I told you in Verilog all the statements are executed in parallel. Okay, so these two statements are executed parallel. Then which one I need to consider here? My driver is driving. Okay, so driver is driving. What is the variable it is driving? A equal to b, it is driving. No problem, this interface will take care of that. Okay, but immediately another person came. B equal to a is mine, he is saying that. He is saying that b is mine, and he is saying that a is mine. Okay, this mouse is whose means this mouse is mine, I am saying that. And then someone is came that no, this mouse is mine, I have bill in my hand. Then I need to judge who, whose mouse is this actually. Okay, this will avoid by this inactive region. Hash zero statements will avoid this one. This means these two statements are executed at the same time, but some little delay is there. That hash zero will gives you light speed delay. So just a small second it will hold that and it is executing that. Okay, both are executing at the same time. That is the inactive region. Inactive region, it is executing, it is avoiding that race condition. Okay, and NBA region. I told you now. So in active region, what is the output you are assigning? Some Q is equals to D. This D is executed in active region, right? Okay. This Q is active executed in active region. But I have assigned the input to my output. But this output is updated in this NBA region. Okay, so output updates occur here. Okay, whatever the updates we are having, all scheduled less than or equal to updates occurred here. Okay, that is the reason, that is the non-blocking region. In this non-blocking region, whatever the left hand side, like q equal to d you are assigning, right? That left hand side, what is the statement you are having? Q. Okay, so this q will be executed here. Okay, this Q will be executed here. In this D will be applied in which region? Active region, right? This Q is applied to, sorry, D is applied to Q, in active region it is applied. Yes. But my output is appeared in some time, okay, that is appeared in the non-blocking region, okay, non-blocking region it is executing. So here we model like flip-flops. So because all the NBA regions are used for procedural assignments. So registers, flip-flops, all these things are procedural assignments, right? For that purpose, this NBA region it is utilized. Why blocking is dangerous for sequential circuits? Because sequential circuits having memory and it depends upon some previous value, and then these blocking statements are executing at the same time, and it is not depends upon any previous value, it depends only on present value. That is the reason it is dangerous. This blocking updates immediately, but non-blocking is not updating immediately. So it is resolving, it is solving in it assigns in NPA region, right? It will take some time. That is the reason real flip-flops do not behave like that. See, NBA solves this problem. Okay. So any blocking statements are there means, okay, that will execute immediately. Non-blocking statements are there means it will execute some other time. Okay. Monitor region means we need to use that dollar monitor, dollar stroke. Okay, so suppose they will ask you the questions like some dollar display statement is there. Okay, this dollar display statement a value will be executed first. Okay, and then same value a equal to 5 we have assigned. I want to update this a equal to 5 value immediately. What is the thing you need to consider? Instead of writing dollar display statement, you need to write dollar monitor or dollar stroke. Okay, dollar monitor, dollar stroke will continuously monitor that. Dollar monitor is continuously monitor whatever the value you are changing. Suppose a equal to 0, I have changed in the first delay. After that, some delay, a equal to 5 I have changed, and then some other delay, a equal to 10 I got that, and some other delay, a equal to 20 I have given. In this way, I am assigning some values, right? So that is the reason I need to monitor each and every change in my simulation time. Okay, in my simulation, I want to observe each and every change. Then I will go for this dollar monitor. This dollar stroke, what is the last updated value is there, that will be printing. That is the reason a equal to 5 is there means this last updated value is printing that. Okay. So print final value after the updates completed. If you changed anything, all the things are updated here. Dollar monitor. This is the monitor region. See, a equal to 0 is executed in active region, and this a is executed in active region, and c equal to 1 is executed in active region. Okay, so and then d equal to a is executed in active region. Okay, all these are executed in active region, and b will be executed in npa region. Okay, so at time t equal to 0, active regions becomes 0 immediately. So in active region a becomes 0 immediately, right? This is the a equal to 0, and then b will be scheduled in the nba region. Okay, and then blocking becomes immediately, that is in active region. Okay, c becomes blocking, c becomes 1 immediately, that is also executed in active region. And this future events like delays you are assigned that, then that is executed in the future region. Okay, some delays are there means in the future region it is executed. Whatever the b value is there, that will be updated in the nb region. Okay, clear?
Yes, sir.
So this is the reason. Active region is executed immediately. Inactive region, some delays are there. NB region, the what is that dollar monitor is there. So printing the final values and future delayed values is there. Okay, NB region, what it is updating here, uh, less than or equal to say equal to LHS side, it is updating in the NB region. Monitor region printing the final updated values. And future region, some delays are there, means this future region will be taking place. Okay, this is the summary. Okay, just read this summary. Scheduling schematic defines how simulation events are ordered or executed inside the simulator accurately. Okay, and modeled digital hardware behavior. That is the reason we are using these scheduling schematics. Each simulation time slots are divided into multiple events regions like Act 2, in Act 2, NBA, monitor and future regions. Okay, so these delays will be executed in future region and monitor region final printing values. Okay, and then NBA region LHS will be updated here. Okay, inactive region hash zeros will be taking place. In active region, all the blocking and then dollar display statements all are executed in this active region. Okay, same thing. Active region executes blocking assignments, evaluates RHS expressions, and then process continuous assignments. Okay, NBA regions delayed updates on the non-blocking statements like so Q less than or equal to T. So this there is a delay updation Q. And monitor regions print the final stable values. Dollar monitor and dollar stroke we are using. And future region, some delays we need to mention. That is the future region. Why these schedulings are useful means it will prevent the race conditions. Clear? Race conditions, and then it will execute the simulation correctly. That is the reason only we are considering this what it called schedulings.